Next up is Wei-Yin, who's going to describe some of the work he's been doing on exploring CNNs on the edge.
All right. Hey, everybody. My name is Wei-Yin, and I'm a MCIT robotics dual degree student. And today I would like to discuss some of the findings that I found while looking into efficient neural networks that can do inference in real time. So, so everybody here knows that how powerful convolutional neural networks are when it comes to performing computer vision related tasks. However, a lot of the research has been squarely focused on accuracy, which makes a lot of these nets too costly to run on edge systems such as a cell phone or a drone. So my focus is in looking into nets that make these speed accuracy trade-offs and see basically how well they work on these types of edge systems. So quickly, I want to mention the criteria. So I looked into nets that do these three types of tasks. So object detection, semantic segmentation, and instance segmentation. And all the nets that I benchmarked were nets that the authors specifically mentioned speed as it's one of the primary focuses. And I also looked into ways to implement these nets that optimizes the system usage. And lastly, all these nets have to work well on the edge. And so this is the edge as far as we're concerned. So basically, I used the Jetson TX2, which is basically a Raspberry Pi on steroids. What it does is that it has a powerful GPU and 8 gigs of RAM. And it's really interesting that the GPU actually uses the system RAM. So it shares the same RAM space as you would in a regular RAM. And also tested out this neural compute stick, which is a very interesting device that lets you offload the computations that you would normally do on the GPU onto this USB stick. It currently works with only TensorFlow and Caffe, and the support is somewhat limited, but I'll go into a little bit more of it later. So these are the nets that I looked into. I had a couple more since I turned my thesis because I had the time to add a couple more. But yeah, let's get to it. So as far as methodology goes, I compared the TX2 benchmarks with my desktop, which is a pretty decent GPU and 6 gigs of RAM. The inputs are coming from either a video camera, from a webcam streaming, and then I was just grabbing frames of the webcam, or it comes from the camera sensor that's built on the TX2's development kit. So the metrics I look into include FPS, GPU RAM utilization, and system RAM utilization, and just a general CPU percentage. And then because the ultimate goal is to make sure that this runs well within the drone for the FLA program. But since there's no labeled data for the footages found on the drone yet, so I used basically data sets that include the things that we're interested in. So for object detection, a common metric is the COCO data set, and it includes the objects that like people, cars, traffic signs that we're interested in, and cityscape, which is what I feel like everybody uses when it comes to self-driving cars. And lastly, I want to mention that I built a little framework that abstracts out the camera devices and the deep learning libraries so that you can basically write a short config file, and then you can plug and play these different hardware devices and use these libraries fairly seamlessly. So check it out if you are interested. So I want to get to the results. So this is some of the benchmarks I got from doing object detection on desktop. As you can see, I got 3 implementations of the SSD mobile net. I think one thing that would jump out is what comes from the Movidius. So the USB stick does what it says it does. It offloads all the computation from the GPU onto the stick, and at 8.5 frames per second is fairly reasonable to use for real-time detection. Unfortunately, as I mentioned before, the software for the Movidius is still fairly lacking, so that you basically can only use the nets that the developer themselves have implemented, which is unfortunate because that means that you can't really build novel networks or just use a layer that it doesn't support on top of it. So that aside, there's a significant difference between the author's implementation of SSD mobile net versus a little hack, if you will, that divides the convolutions, keep it on the GPU, whereas the post-processing is done on the CPU split. As you can see, like while keeping the system resource usage is roughly the same, it was able to improve the speed by almost twice as fast, which was pretty exciting when I realized that that's possible. So MobileNet v2 and YOLO v3 are all released, I think, last month. So I was able to get some benchmarks in. The MobileNet v2 was able to get very good speed right out of the gate and no hacks involved. But it also uses considerably more RAM on the GPU. Whereas YOLO v3 is generally slower, but because the author himself basically built his own deep learning library, he was able to keep the whole program running real small, as you can see in terms of like the RAM and CPU percentage. And also the most accurate net out of the Subway benchmark. So these are the results for the TX2. Much of the speed and whatnots are still holds. The GPU-CPU split is still the fastest by roughly the same factors. YOLO v3 got a lot significantly slower. But yeah, it's basically the same results as you've seen before. Just a lot slower, I guess. But okay, so this is for semantic segmentation. ENet is extremely fast while using basically the same amount of system resources as EarthNet. However, it does so at a pretty noticeable penalty to the accuracy, as you can see from the MIOU based off the Seascape dataset. While EarthNet is a pretty distant second, it maintains a lot of the accuracy compared to all the other fast models, if you will. I included the ResNet 18 and 34 implementations, which uses the ResNet as the encoder, and then decoder is just like a bilinear interpolation, because I want to show how efficient design actually matters. EarthNet and ResNet 34 have roughly all 30-something convolutional layers, and their architectures are extremely similar. The only difference is that EarthNet factorize all its convolutional layers, so that and you can see that just by doing that very small modification, you can basically increase the speed by a factor of 3. And yeah, I also was able to get a MobileNet v2, DLET v3, I know, great name, for just like get it in the last week, and the results just wasn't as good as I thought it would be. So these are same nets on the TX2. Again, the ideas still hold. One thing that I thought was interesting is that when I tried to get the ResNet implementations on the TX2, the TX2 really doesn't like the decoding part, the bilinear interpolation part. So I ended up having to really just like use like nearest neighbor, because at this point these nets are just not going to be used, and to even get these benchmarks. But that was not a problem for either ENet or EarthNet. Okay, so for instance segmentation, there's actually not that many models out there. I found one that uses mass RCNN with instruction v2 as the feature extractor. That's the fastest of the ones that are available. And it is really fast at 16 frames per second on desktop, but it also is a system hog. It uses basically the entire GPU space, and then also on top of the regular system RAM, which makes this infeasible to run on the TX2. So basically, what I noticed about the common variable of designs is that all these nets that emphasize speed reduce the input size or fix it to some certain resolution really early on. The problem doing that, obviously, is that it really takes a huge impact on accuracy. So this is one of the main speed versus accuracy trade-offs I see in these nets. And the other one is that they all use some ways to reduce the parameters when it comes to convolution. And so the one that the picture I included is from EarthNet, which is a pretty, shows a really easy way of how you would implement factorized convolution. you just break the 3x3 filters into 1x1 followed by 1x3. That's that's the main thing it did to really improve the speed. And this picture truly doesn't show you much at all because I didn't think about how it would look on the screen. But basically, what I was trying to show you is that how if possible, model-specific optimizations are really powerful. So this is from the splitting the mobile nav from like pure GPU into GPU CPU, and then like it really takes out. So the post-processing steps are like the TF wear and just like the non-max suppressions for the getting the boxes. Yeah, those somehow run a lot better on the CPU than on the GPU. So yeah. I just wanted to mention that I guess what I learned is that it was really shocking to me how heavy the deep learning libraries are just to run it. This goes for like TensorFlow and PyTorch and basically all the other like Caffe2 as well that I tested. That was pretty surprising to me, and also it was not very obvious, which I thought would, when it comes to speed accuracy trade-offs, as you can see from eNet versus EarthNet. I think a lot of it will become very task dependent on whether like how you want to deploy these nets, and and also one thing I also want to address is that a lot of these nets come from within the same 8 months that I've been working on this project. So basically, there's suddenly a big surge of popularity when it comes to building neural networks that are actually efficient. And I think a lot of it relates to what smart devices can do nowadays. Lastly, I want to mention that in the future, I think like there's some specific design techniques, like including like pruning, which involves ranking the neurons and removing the ones that don't contribute. That I've read that was able to significantly reduce both the memory footprint and improve the speed. And also, there's all these different lightweight libraries that are coming out, and like and NVIDIA is doing a TensorRT that's supposedly really optimized running nets on their platform. But yeah, anyway, this is my findings. Thank you all very much, and I'll leave room for questions.
These are all the same precision, all the implementations, or like in terms of when you run the same algorithm, you're getting exactly the same results, or are there some differences in fixed points and fixed point precision or floating point?
So can you
so when you run the same algorithm on a different platform,
right?
Are you getting exactly the same floating point kinds of
right.
implementations? Everything's the same, or no?
So it's mostly the same. The only difference is that on the TX2, sometimes the decoder parts don't work as well. The whole for eNet EarthNet was able to get the same precisions, but for the ResNets, they just straight up just did not work at all. So other than the ResNet, other than ResNets, the other ones will definitely hold.
But the ResNets didn't work.
Yeah, the ResNet just didn't work. Yeah. All right. All right. Thank you.